Please settle down. So we'll have a crisp discussion on some rudiments of nuclear physics today. So you know there are two sides of nuclear physics. On one side is physics and on the other side is chemistry. And we'll not cross over to chemistry. Right? We'll stay in the nuclear physics. So, as obviously the name suggests, and as all of you already know, nuclear physics is about events associated with the nucleus. All events associated with the nucleus, related stuff, that will be part and parcel of our nuclear physics digressions. And the nucleus, again, is essentially a densely packed spherical region. A very densely packed spherical region housing protons and neutrons. Right? Housing protons and neutrons. Very densely packed region housing protons and neutrons. And if A is the atomic mass number, A is the atomic mass number, which you know is essentially number of neutrons plus number of protons. Z henceforth will be used to designate number of protons. And N number of neutrons. And A is the atomic mass number, which is the sum of neutrons and protons. Now, this very densely packed region, has a certain average radius, and I'm not going to derive that result for you. This average radius of this densely packed spherical region is like some R naught, A to the power 1/3 A is the atomic mass number, and R naught is a constant. Are you aware of this unit called femtometer? Do you know what a femtometer is? A femtometer is like a unit of measurement of distance used in nuclear physics. A femtometer is essentially 10 to the power minus 15 meter. That's a femtometer. That's a femtometer, FM, 10 to the power minus 15 meters will constitute a femtometer, right? This order of magnitude becomes relevant in nuclear physics. This R naught is 1.2 femtometer. This R naught is 1.2 femtometer. A is the atomic mass number. Then the average radius of the nucleus is given by R naught A to the power 1/3. R naught is this constant, 1.2 into 10 to the power minus 15 meters, right? Now, there are some critical issues related to the nucleus. And while we are dealing with the nucleus and its constituents, like I said, are protons and neutrons. And together, protons and neutrons, they constitute what are referred to as nucleons. The residents of the nucleus are called nucleons. The residents of the nucleus are referred to as nucleons. Now, when we are talking about a nucleus, there are two things to bear in mind. One, these protons, as you are aware, are positively charged particles. They are positively charged particles. And these protons, they exert on each other very large electrostatic repulsion. You know, electrostatic forces are long distance forces. They exert on each other very large electrostatic repulsion. And large enough for them to tear apart the nucleus. They could essentially tear apart the nucleus because of very large electrostatic repulsion. What holds them together then? The question is, what holds them together? Now, there are these distance forces that exist between nucleons, which are charge independent. They do not depend on the charge. That means, the short distance force that I'm talking of will be the same between two neutrons, between a proton and a neutron, between two protons. These short distance forces are attractive in character. These short distance forces are attractive in character and are referred to as nuclear forces. They are nuclear forces. Switch it off. They are attractive and they counter the electrostatic repulsion. They counter the electrostatic repulsion. Again, not getting into too much of nitty-gritties of this nuclear force, except that, let me tell you, this is not a central force. It's not a central force, and it will not allow conservation of orbital angular momentum, etc. So, in any case, these are short distance forces. These are short distance forces. They are attractive in character, and they do not depend on the charge of the particles that associate nuclear forces with each other. Right? Now, most nuclei referred to as nuclides have a very typical feature. They are unstable. When I say they are unstable, what it really means is that they mutate into other nuclei. They mutate into other nuclei using some transformations, bringing stability to the nucleus. Essentially, there is a certain combination of neutrons. There are three things: the neutrons, the protons, and the size of the nucleus. Neutrons, protons, and the size of the nucleus. Based on a combination of things, there is an appropriate, so protons let me designate by Z henceforth instead of P, Z, right? N is the number of neutrons, Z is the number of protons, and there is a size of the nucleus. There is a certain apt combination of the three parameters. Which brings stability to the nucleus. Transcending those parameters will bring about instability to the nucleus. One nucleus then mutates or transforms into a more stable nucleus. And a certain set of events accompany this transformation. Now, even before I get into that, look, when a nucleus gets constituted, nature would have constituted this nucleus somehow, right? They would have been originally, say, these nucleons, the neutrons and protons spread apart, right? And then nature would have had to do something to put them together in this region, to bind them together in this region. Nature would have had to do something, right? Essentially, if there were n neutrons and there were z protons, right? Then there is a total mass of this widely separated neutrons and protons. The mass of these nucleons, would have been the mass of a proton into number of protons, Z, right? Plus mass of a neutron into A minus Z. A is the atomic mass number. That would have been the sum of the mass of the constituents. That would have been the sum of the mass of the constituents, the nucleons for a given nucleus, when they were far apart, right? However, again, you know, there are certain things that we would have to keep in the black box. But what happens is, when these particles go ahead and constitute the nucleus, when the protons and the neutrons constitute the nucleus, the mass of the nucleus would have been less than m. If this was m, the mass of the nucleus would have been less than m, where m was the separate masses obtained when the nucleons were far apart, right? There is a reduction in mass. There is a mass reduction from these separate constituents. When the nucleus was constituted out of the same constituents, there was a reduction in mass. There was a fall in mass. Same particles, but the mass decreased. And when the mass decreased, so essentially, you know, this loss of mass in constituting the nucleus, is called a mass defect. This loss of mass is called the mass defect, which is like delta m, the change in mass. From these separated constituents to the constituents of the nucleus, there is a mass defect, delta m, which would be this mass, which is small m, minus the actual mass of the nucleus. That's the mass defect. That's the loss in mass. Essentially, if there is loss in mass, it must have featured in some form or the other. If there is this loss in mass, it must have featured in some form or the other. This loss in mass, actually, that you see here, is manifested as energy. This loss in mass gets manifested as energy, E, which is delta m into c squared. This is the Einstein's equivalence energy mass conversion. So the mass defect that you see here translates into this amount of energy. Sees the velocity of light. So which means, when this transformation took place from the separated constituents to the nucleus, there was liberation of energy. There was loss of mass and there was energy liberated. This energy was liberated. And this energy which is liberated is called the binding energy. This is called the binding energy of the nucleus. Delta m into c squared is the binding energy of the nucleus. And so every nucleus has a certain binding energy which can be obtained as delta m mass defect into square of the velocity of light. So this nucleus has a certain binding energy, right? What it also means is, now if you want to separate its constituents, you would have to supply this amount of energy. In order that you could separate its constituents, right? There is an important entity in terms of stability of the nucleus. Very largely, the stability of the nucleus depends on a quantity called binding energy per nucleon. Nucleon means the total number of protons plus neutrons. Total number of protons plus neutron will constitute the nucleons. So binding energy per nucleon is like EB, that's the binding energy of the nucleus, divided by the atomic mass number. The atomic mass number will tell me the number of neutrons plus number of protons. This binding energy per nucleon. Greater the binding energy per nucleon, the greater would be the stability of the nucleus. The greater the binding energy per nucleon, not the binding energy per nucleon, greater will be the stability of the nucleus. And typically, the binding energy per nucleon versus atomic mass number A. Binding energy per nucleon versus the atomic mass number has a variation like this, roughly. And you see, this is a preferred region for stability because binding energy per nucleon is large here. And this is the region where the atomic mass number varies from roughly 50 to 60. Atomic mass number varies from 50 to 60 in this region. So essentially, you know, when a nucleus is unstable and it wants to acquire stability, you know, it would ideally want to belong, it's the disintegrated nucleus would want to come to this regime, 50 to 60, atomic mass number 50 to 60, because then the binding energy per nucleon is maximum, which provides greater stability to the nucleus. This is what happens. Now, it's a decreasing, it decreases after that. This is versus atomic mass number, it decreases after that. Binding energy per nucleon decreases. This is the variation of binding energy per nucleon versus atomic mass number. That decreases, right? So this is the region where you find maximum binding energy per nucleon. So this is a preferred region for stability. So if there are two nuclei, one with greater binding energy per nucleon, then that nucleus will have greater stability. It would maintain its status. The status of the nucleus is what? The status of the nucleus is, there are two things. The number of neutrons and the number of protons. Right? That's the status of the nucleus. It would then want to, if it's stable, it would want to maintain that status. Right? If it's unstable, it would like to have a different combination of neutrons and protons. To get stability, it would like to have a different combinations of neutrons and protons. That will bring it stability. So now, mass numbers. So this is per nucleon. Now, so these are again, you know, these are benchmarks. All these rules will be primarily empirical. There is also, you know, an empirical rule about neutron to proton ratio lying between 1 to 1.6, which brings about stability, and greater than 1.6 bringing it making it unstable. There is a rule, but again, that's a thumb rule. There are limitations on that rule. That's primarily empirical. If neutron to proton ratio is roughly lying between 1 to 1.6, that nucleus is mostly stable. Greater than 1.6, it could render that nucleus unstable. But there are more parameters than just this. There is also something about the size of the nucleus and other things. So, in any case, one way or the other, an unsuitable combination of neutrons and protons in the nucleus is likely to bring it instability. Sometimes it's unstable because the nucleus is very heavy, size of the nucleus is large. Sometimes it's unstable because the number of neutrons exceed the number which is required for stability. Sometimes there is instability because there are more protons than what is required for stability, and so on and so forth. So different things would cause different events for a transformation or lack of it. Now, so if a nucleus is unstable, one reason is the size of the nucleus. And if size of the nucleus is an issue, too large a nucleus, then how a nucleus responds it. There is a nucleus X, right? It has atomic mass number A, it has atomic number Z, number of protons. Number of neutrons would be A minus Z. Then what it would do is, if it's a bulky nucleus, it would shed away some of its protons as well as neutrons. It transforms itself into another nucleus Y. And it emits out of the system, ejects out of the system particles that are referred to as alpha particles. Alpha particles are essentially helium nuclei. What's a helium nucleus? Mass number 4 and atomic number 2. So it has 2 protons and 2 neutrons, right? That's a helium nucleus. So which means atomic number must have reduced by 4. So A minus 4 would be the atomic number. Number of protons must have reduced by 2, Z minus 2. So this species, this nucleus, transforms itself to another nucleus Y, which is a stabler nucleus than X, by emitting these particles, the helium nucleus. This is a helium nucleus. It's a helium nucleus, which is, obviously you can see it's positively charged. It has 2 protons and 2 neutrons. It's positively charged. It's a helium nucleus, positively charged. And a positively charged helium nucleus, and this is called an alpha particle. So species X transforms to species Y with atomic number reducing by 4, with mass number reducing by 2, accompanied with emission of alpha particles. So this alpha emission is primarily related to the bulk of the nucleus. Too bulky a nucleus, it will take a recourse to emission of alpha particles, which are positively charged helium nuclei, right? So that's one kind of transformation that takes place in order to, with a view to acquire stability. Nucleus Y will be more stable than nucleus X. Now, there are times when instability could be because the number of neutrons in the nucleus are larger than what is required for stability. The number of neutrons are larger than what is required for stability. So sometimes instability would be because of excess number of neutrons. Than those that are required for stability. So then, and by the way, all this phenomena of generation of these particles, it's entirely a nuclear phenomena. It has nothing to do with the revolving electrons. All of this happens within the nucleus. All of this transformation happens within the nucleus, right? All nuclear phenomena. And almost independent of temperatures and pressures, almost independent of temperatures and pressures. So then, if the problem related to stability is with the neutrons, then a neutron will oblige, it will relinquish its status. What a neutron then does is, if there are excess number of neutrons than what is required for stability, then a given neutron transforms itself into a proton. Transforms itself into a proton. Transforms itself into a proton, followed by fast moving electrons. These are fast moving electrons. And until long, when people were studying particle physics, this kind of a transformation of a neutron to a proton and a fast moving electron could not explain some facts related to energy and momentum. Some facts related to energy and momentum could not be obtained until a very long time. And then they figured out that, hey, this transformation is accompanied with yet emission of another kind of particles called antineutrinos. Antineutrinos. Antineutrinos are these particles, and they account for the difference in momentum and energy in the transformation. And for long, these particles could not be detected because they did not interact with matter. Because they did not interact with matter, they could not be detected. So, in any case, this is an antineutrino, and we will not break our heads on, how the characteristics of antineutrinos. All that I want to tell you is that they suspected presence of these particles because they could not explain this transformation all by itself on the energy and momentum domain. And inclusion of an antineutrino explained the difference in linear momentum and angular momentum and energy. So these are antineutrinos. So these are fast moving electrons that are emitted, and this proton remains in the nucleus. This neutron has transformed itself into a proton. The proton remains in the nucleus, right? That means even though one neutron has been lost, one atomic mass number has decreased, but one has increased. So atomic mass remains the same, right? But atomic number increases by 1. Atomic number increases by 1. And these fast moving electrons, they are called beta particles. They are called beta particles. These fast moving electrons are beta particles. Beta, and this kind of an emission is called beta minus negative beta emission. Negative beta emission. It happens when you have more neutrons than that are required for stability. Then a neutron gives up its status, acquires the status of a proton, accompanied by emission of fast moving electrons that are called beta particles. These beta particles are negatively charged particles, and some antineutrinos, to account for energy and momentum. This is beta emission, negative beta emission. This is negative beta emission. So what happens when there is a beta emission that takes place? So I have a nucleus X with atomic mass A and mass number Z and atomic number mass number A and atomic number Z. Then what a beta transformation does is, beta emission does is, it transforms this into a nucleus Y. A will not change, but number of protons have increased by 1, so Z will become Z plus 1. This is what would happen in a beta emission. This is what would happen in a beta emission. Beta particles emitted, mass number unchanged, but atomic number increases by 1 because of an excess proton produced in the nucleus. And in alpha emission, these are alpha particles, these are beta particles. One of the things that I need to tell you is that these alpha particles and beta particles both have some penetration powers, but the penetration powers of these beta particles is lot more than the penetration power of these alpha particles. Beta particles will penetrate lot more than penetration of these alpha particles. So that's the beta negative emission. That's the beta negative emission, right? And then there is a positive beta emission. There is also a positive beta emission, beta plus emission. Most of the time when they talk of beta emission, they are actually referring to beta minus emission, negative beta emission, which is what I just discussed. Fast moving electrons, referred to as beta particles, that are emitted along with a neutron transforming itself into a proton within the nucleus. Again, a nuclear activity only, activity in the nucleus itself, right? And then there is a beta plus emission. When the problem lies in having more number of protons than what is required for stability. If the problem with the nucleus is that, hey, it would have rather wanted fewer protons. It would have rather wanted fewer protons. Because it's unstable because of more number of protons than what is required for it to be stable. Then a proton obliges. It is ready to give up its status. A proton is ready to give up its status. What a proton does is, so if I have a proton P, it transforms itself into a neutron. It transforms itself into a neutron, followed by emission of a very special class of particles called positrons. E plus is a positron whose charge is the same as the charge on an electron but positive, and negligible mass. A positron has the same charge as that of an electron but practically zero rest mass. That's a positron. And followed by, again, to account for momentum and energy, there are neutrinos. Those were antineutrinos. This time these are neutrinos. This is a neutrino. So that is beta plus emission. That's a beta plus emission. And what has happened in a beta plus emission? A proton transforms itself into a neutron. Beta plus emission would occur if the number of protons are more than what is required for stability, followed by emission of a positron. Most of the time when they talk of beta emission, this is what they are referring to. Now. And in beta plus emission, so suppose there is a nucleus X whose mass number is A and whose atomic number is Z. When it undergoes a beta plus emission, what happens to the mass number? It remains the same. What happens to the atomic number Z? It decreases by 1 because one proton has reduced. So it's going to become Z minus 1. This is what happens in a beta plus emission. Sorry? I will not be able to answer this question right away. It's actually not that easy a question to answer. If they are stripped of their energy, can they be put? Theoretically, yes, is what I would say. Stripping them of their energy, you can put them, but I wouldn't be very sure of this right now. I mean, I would want to think that will happen. And again, these are electrons that have not come out of revolving electrons. This is a certain transformation that has happened. Whenever this neutron to proton and proton to neutron transformation takes place, the reason they are different, protons and neutrons in the nucleus, is because they are surrounded by a cloud called the meson cloud. MESON, meson cloud. And so it is changes. There is a pi plus meson and there is a pi minus meson, and which is what results in this transformation. But again, that's getting into particle physics too much, and we will unnecessarily get it open the Pandora's box. So these essentially, these electrons have not originated out of the orbits. They have not originated out of the orbits. Now, so far so good, right? Now, see, every time a transformation, so, this transformation that has happened, this transformation that happens from a nucleus X to a nucleus Y, this transformation can take place because of, from X to Y, it can take place because of emission of alpha particles. It can take place because of beta particles, alpha particles, beta particles. Now, whenever a nucleus X transforms into a nucleus Y, we say there is a decay. We say there is a decay. It's called a radioactive decay. It's called a radioactive decay. And why does it happen? To bring more stability, to the system. Again, Y could further transform into Z. Y could further transform into Z because Z would be more stable than Y, right? So, whenever this radioactive decay happens, it could either be because of emission of alpha particles or emission of beta particles. What happens is, see, first of all, this nucleus is called the parent nucleus. This nucleus is referred to as the parent nucleus. This nucleus is referred to as the daughter nucleus. Obviously, the daughter nucleus will be more stable than the parent nucleus. So, whenever this happens, be it because of alpha emission or beta emission, the daughter nucleus is actually in a very excited state. The daughter nucleus is in an excited state. No matter what causes it, the alpha particles or the beta particles, emission, the daughter nucleus is in a very high energy state, Now, it doesn't, obviously, no particle likes to be in a high energy state. It now lets go of this, it'll let go of this energy to come to a ground state or a lower energy state. It'll want to come to a lower energy state, call it Y. That's a lower energy state. Without change of species, the species is Y only, right? But it relinquishes its energy. High energy state, very excited state, it goes to a lower energy state. Less excited state could be a ground state. No matter what has caused this transformation, emission of alpha or emission of beta, this transformation will occur. And when this happens, there is loads of energy released, right? And that energy is perceived to be what is called gamma rays, gamma radiations. Gamma. Yeah, I'll tell you. So from high energy state, the species wants to get into a lower energy state, right? Which means it would have to let go some energy in the form of some electromagnetic waves, and those waves are in the form of what is called gamma radiations. The wavelength of the rays, how we know these are gamma radiations? Because they are minimum wavelength. You know, in the electromagnetic spectrum, you start with radio waves and you end up with gamma rays, which are the minimum wavelength electromagnetic waves. This is minimum wavelength. In the electromagnetic spectrum, this is minimum wavelength. But, sorry? Minimum wavelength, but they are very high on energy, high energy minimum wavelength radiations. And these radiations, these gamma waves, are lot more penetrating than the beta particles. They are a lot more penetrating than the beta particles. They find application in medical science. They find application in medical science. Emission of these gamma rays, very low wavelength means high frequency and very high amounts of energy. They carry very high amounts of energy. Because of the high amounts of energy that they carry, they are trenchant. They are extremely penetrating, lot more than the beta particles, In fact, gamma waves across the Milky Way, the universe, they are created out of very exotic energy events. High energy events result in formation of gamma waves anywhere in the universe. A very exotic energy event will result in formation or release of gamma waves. So gamma waves are always associated with very high energy. So be it due to alpha particles or beta particles, the nucleus, the daughter nucleus, would be in an excited state. To come to a ground state, it would release large amounts of low wavelength energy, which is gamma waves. So gamma radiations, a transformation from X to Y will always more or less be accompanied with emission of gamma waves or gamma rays, right? Now, so there is a large sample of particles, nuclei, n nuclei, radioactive nuclei, and there is going to be a decay. That happens here. There is going to be a radioactive decay that happens if it is unstable. Say a nucleus X transforming itself into a nucleus Y. Each of these n nuclei would transform into some other nucleus Y. N obviously will decrease with time. And you know, of these large nuclei, one can never predict which one will first undergo this transformation from X to Y. Right? It's a statistically random phenomena. No one can predict which of the n nuclei will first undergo transformation. But the important thing is that there is a rate at which this decay is taking place. That means there is a dn dt, which is the rate at which n is changing with time, which is rate of decay. But n is decreasing with time, so dn dt is a negative number. So minus dn dt is the rate of decay. At a given instant minus dn dt is the rate of decay, and it's called the activity at that instant. Minus dn dt is called the activity at that instant of time, which is like, as you can see, decays per second, at that instant. Decays per second, right? This is decays per second, which will tell me how many nuclei are decaying every second at that instant of time. This is what it will tell me. No, it will not remain constant. It will be a function of time, as I am going to very shortly demonstrate. This activity will be. So decays per second, this is measured in a unit called becquerel, BQ. which is my SI unit for decays per second, becquerel. Becquerel. 1 decay per second is 1 becquerel. Per second is 1 becquerel, BQ. Obviously, it's a very small unit. It's not like one nucleus is decaying every 1 second. That's not. A more practical unit of measurement of decays per second is a Curie, given by Ci. Curie, given by Ci, and 1 Ci is 3.7 into 10 to the power 10 becquerel. 10 to the power 10 decays per second, DPS. We can call them DPS, decays per second. This is what DPS does. There is decaying in DPS. With every DPS, there is a number associated here. So, and there is another unit called Rutherford, RD, which is like 10 to the power 6 decays per second, or 10 to the power 6 becquerel. These are two practical units of measuring decays per second, Curie and Rutherford. This is Rutherford. He's made his presence everywhere. Name it. So now the decays per second. Would you not want to believe that if n was larger, then the activity would be more, decays per second would be more. If n was larger, then decays per second would be, if you double n, the decays per second will get doubled. The activity level would get doubled. If you halve the number of nuclei, then the activity level will get half, decays per second, right? Will depend on the population of the nucleus. The activity will be directly proportional to the population of the nucleus. So which means activity which is minus dn dt will be proportional to the population of the nucleus at that instant of time. Will be proportional to the population of the nucleus. Obviously, since n is changing with time, you would expect A to be changing with time. You would expect A, the activity dps, to be changing with time, right? And this we can write as minus dn dt equal to some lambda n, constant of proportionality into n. Lambda is called a decay constant. Lambda is referred to as a decay constant. And of course, this decay could have happened because of one or more reasons, alpha particles, beta particles. There could be different processes causing decay. But no matter what, the activity level will be proportional to the total population of the nuclei at that instant of time, right? Now, if at time, so this is n nuclei at an instant of time t. This is n nuclei in this sample at an instant of time t. If at t equal to 0, n was n naught, right? We started with n naught nuclei at an instant of time t equal to 0. We started with n naught nuclei at an instant of time t equal to 0. Now let's carry out an integration. dn by n is minus lambda dt. Yes or no? We could then integrate both sides. When t is 0, n is n naught. When t is t, n will be n. Right? Which will give me log n by n naught is minus lambda t, or n would be n naught e power minus lambda t. That's number of particles at any given instant of time t is given by this. As t tends to infinity, n tends to 0. As you can see, at t tends to infinity, n tends to 0. At t equal to 0, n is n naught. So there is an exponential decay of the nuclei, right? there is an exponential drop in the number n. There is an exponential drop in the number of, so these are living nuclei. These are living nuclei at an instant of time t. We started with n naught at an instant of time t. The number of active nuclei, the original nuclei, not the transform nuclei, the original nuclei would be n. N is the number of original nuclei left in that sample, waiting to get decayed, right? So n with t at t is an exponential dip. At t equal to 0, n is n naught. Now the n is the number of active nuclei at an instant of time t. Sooner or later all these nuclei would get decayed into some other species, Lambda is the decay constant, like I said. Obviously, the activity level is minus d and dt. The activity level will be given by minus d and dt, right? Minus d and dt, which is like, if I differentiate this with respect to time, lambda n naught e power minus lambda t. Yes or no? What minus? Minus d and dt. So minus will get cancelled, right? At t equal to 0, n is n naught. So what would be the activity level at t equal to 0? A0 would be proportional to n naught. Activity level at time t equal to 0 would be a naught, which is lambda n naught. Yes or no? So lambda n naught is the activity level decays per second at time t equal to 0. At t equal to 0, isn't it? Activity is proportional to n. Activity at any given instant of time would be lambda into number of active nuclei at that instant of time in the population. So if I differentiate n with respect to time and I plug in a minus sign, the minus will eat up the minus, right? So lambda n naught is activity level at time t equal to 0, decays per second at the initial instant of time, starting with n naught untouched nuclei, right? Undecayed nuclei. So activity level as a function of time again is exponential. At t equal to 0, activity level is A0. A0 is, so this is like A0 e power minus lambda t, where A0 is the initial activity lambda n naught. Initial decays per second, which is lambda n naught. Yes or no? Not a problem? Now, can I wipe this off? So we have n is n naught e power minus lambda t, right? We started with n naught and now we are left with n. We started with n naught samples of the nuclei and now we are left with n. So how many have got decayed? N naught minus n have got decayed. So number of nuclei decayed up to t is n naught minus n, which is n naught minus n naught e power minus lambda t is the number of nuclei decayed, which is n naught into 1 minus e power minus lambda t, right? So the number decayed as a function of time, the number decayed, this is n number decayed up to an instant of time t. Obviously at t equal to 0, nothing has decayed, so n will be 0. It's like charging of a capacitor. Do you realize? It will eventually n naught will get decayed. By infinity, n naught would have got decayed. This is the variation of number decayed as a function of time. Number decayed as a function of time is what you get. Right? Now, look, the number of active nuclei as a function of time is this. We started with n naught nuclei and it will dip exponentially. Number of active nuclei will dip exponentially to 0 at time t equal to infinity. There is an instant of time when the number of active nuclei will become exactly half. There is an instant of time t when the number of active nuclei will become exactly half. And this time is called the half-life of the sample. This is called the half-life. Half-life. When the number of nuclei will become exactly half of what we started. That's called half-life. T half. Which means if I have n equal to n naught e power minus lambda t, I want to find t half. So I will put n equal to n naught by 2 and t equal to t half. I'll be able to solve for t half, isn't it? So n equal to n naught by t is n naught e power minus lambda, and t will become t half, half-life of the sample. This is called the half-life of the sample. Do you realize what I've done here? Now if you take the logarithm, then it will give you t half as ln2 divided by lambda. Lambda is my decay constant. T half is ln2 divided by lambda. Lambda is the decay constant. ln2, this is log 2 to the base e. Its value is roughly 0.6931. You've done this in chemistry so many times. You would know it more than I do. Right? So half-life of a sample is 0.6931 divided by its decay constant. Right? So if I started with n naught samples, then in one half-life, the number of active samples will be this much in one half-life. Right? Now, another half-life, it will become another half of this, 2 half-lives, 3 half-lives, n half-lives. The number of samples will be these many. So if I started with n naught and I look at n half-lives, and if I look at n half-lives, then I'll have the number of active samples as n naught half to power n. N naught half to power n. Very clearly. Right? In n half-lives. Simple, isn't it? Very simple. Now, it is also possible that if I have a radioactive sample, this is a radioactive sample, large number of nuclei n. It decays, it could decay through multiple processes. Say it could decay through 2 processes. There are 2 processes that could lead to decay. One process has a decay constant lambda 1 and another process has a decay constant lambda 2. There is a decay constant lambda 1 of one activity that could lead to decay. There is another activity which could also realize that decay could happen due to multiple activities, due to different things, right? It could happen because of different things, say. So one event has a decay constant lambda 1 associated with it. Another has a decay constant lambda 2 associated with it. Now if I look at a nucleus, if I look at one nucleus, right? So all that I can tell you is it's the probability that it will decay in the next dt seconds. The probability that it will decay in the next dt seconds. If I focus on one nucleus, the probability that it's going to decay in the next dt seconds will obviously be proportional to the decay constant. The greater the decay constant, greater would be the activity, greater the probability that a given nucleus that you are eyeing will decay, right? So the probability that this nucleus decays through this process, probability that this nucleus decays through this process will, number one, be dependent on lambda 1 and will depend on the time span dt that you are looking at, will depend on the time span dt. If you look at a greater time span, then the probability that it will decay in that time span will be greater, right? So the probability that it decays through this process is going to be lambda 1 dt. That's a probability that a given nucleus decays through this process. The probability that it decays through this process will be lambda 2 dt. The probability that it decays through this process is going to be lambda 2 dt, right? So the probability it will decay through this or that is going to be this plus this. Whenever you say or, you add, right? The probability that it decays through this process is lambda 1 dt. So it will either decay through this process or decay through that process. The probability that it decays through this process is going to be lambda 2 dt. The probability that it decays through process 1 or process 2 is going to be lambda 1 dt plus lambda 2 dt. Yes or no? Right? Which means now what I do is, suppose the two processes have an effective decay constant lambda. Suppose the two processes have an effective decay constant lambda. Suppose the two processes have an effective decay constant lambda. Then if lambda is the decay constant, then the probability that the nucleus will decay in dt seconds, given that the effective decay constant is lambda, effective net decay constant is lambda, then I can say the probability that this nucleus will decay in the next dt seconds is this. But this is either because of this or because of this. This is either because of this or because of this, right? So that gives me like a lambda equal to lambda 1 plus lambda 2. That means if number of processes could lead to decay of a nucleus, then the effective decay constant is going to be sum of the decay constants. The effective decay constant is going to be sum of the decay constants for that sample. That's a very important relationship. Very important relationship. Now, if the half-life for this is T1, T1 is the half-life for this, say, right? And T2 is the half-life for this process. And T is the effective half-life. If T is the effective half-life, right? Then realize lambda would be, see, I told you, half-life is given by log 2 by lambda. So lambda is given by log 2 by half-life, right? So if the net effective half-life is 2, then this lambda is what? Log 2 by the effective half-life t. And this lambda 1 is going to be log 2 divided by the half-life t1 plus log 2 divided by the half-life t2. So if T1 and T2 are the half-lives of these two processes, then the effective half-life T is given by 1 by T1 plus 1 by T2. The effective half-life is given by 1 by T is 1 by T1 plus 1 by T2. That means T would be T1 T2 by T1 plus T2. If T1 and T2 are the two half-lives in the two processes, then for this sample the effective half-life can be given by this T1 T2 by T, which means now if I have to write the equation of decay for this, then the number of samples at any given instant of time T is going to be the initial number of samples e power minus lambda effective, which is lambda 1 plus lambda 2 into T, where lambda is lambda 1 plus lambda 2. This is how you would write the equation for this decay. The number of active nuclei at any given instant of time is going to be n naught into e power minus lambda t, where lambda is the lambda effective, which would be sum of the lambdas, And if you know the effective lambda, then you know the effective half-life for this sample, right? Clear? Now, can I wipe this off? Fairly simple, isn't it? See, the number of active nuclei n at any given instant of time is given by n naught e power minus lambda t, where lambda is the decay constant for the process, right? So what I started with was at time t equal to 0, there were n naught nuclei, right? And this sample got radioactively decayed, being reduced to, at an instant of time t, there were n active nuclei left over. I now want to find the average life of the sample, the mean life or the average life. I found the half-life of the sample, log 2 by lambda. I want to find the average life of the sample or the mean life of the sample, right? Say, in the next dt seconds, dn nuclei decayed, n minus dn nuclei left over, dn nuclei decayed in dt seconds. Let me call it mod dn, because if I take dn from here, I'll get a negative number. But I'm talking of the actual number, decayed, magnitude of the number. Dn is the number of nuclei decayed. If I take the differential, this is going to give me minus n naught lambda e power minus lambda t, right? But I'm looking at the magnitude of these nuclei. Which is magnitude of dn, which is n naught lambda e power minus lambda t, right? Yes or no? Now these many nuclei dn, I'm focusing on these dn nuclei which decayed from t to t plus dt. These magnitude of dn nuclei lasted for t seconds, yes or no? Lasted for t seconds. These magnitude of dn nuclei lasted for t seconds. And then in the next dt seconds, they got decayed. They got transformed into a more stabler nucleus. So this total life of these DN nuclei must have been what? The total life of these DN nuclei, because they lasted for T seconds, is mod DN into T, is the total life of these DN nuclei. Yes or no? That must have been the total life, right? What I want to find is, so this is number of nuclei into time, number of nuclei into time. Time for which they lived, time for which they lived for these many T. This is normally years, right? So we are not talking seconds now. Radioactive decay, you know, if it's a natural process, we are talking years, time involved. So then they lasted for these many years, say, or whatever, these T seconds or time T. Some of the total lives of N0 nuclei, some of the total lives of N0 nuclei was when N changed from N0 to 0. When N changed from N0 to 0, there will be the total life of N0 nuclei. Yes or no? And then I want to find the average life for a nucleus. This is the total life for N0 nuclei. This is the total life for N0 nuclei. The average life of a given nucleus would be total life divided by the number of nuclei that I started with. Yes or no? This then would give me the mean life or the average life of a nucleus. Average life of a nucleus. Different nuclei decayed at different instants of time. They actually had different lives. But this is the average life of a nucleus in this sample. This is the average life of a nucleus in this sample. Yes or no? So this is like now mod dn I can write in terms of dt. There is a dt which I should have incorporated. Mod dn I can write in terms of dt as n0 lambda e power minus lambda t dt. So in this case n was my subject of integration. Now t has become my subject of integration. Realize when the number of active samples change from n0 to 0, time changed from 0 to infinity, because in infinity the number of active samples became 0. Yes or no? It completely decayed in infinite time. So t changed from 0 to infinity. I mean, you can see that from here also, isn't it? N is 0 when t is infinity, n is n0 when t is 0. So I have gone from the n domain to the t domain. That's the total life divided by n0. That will be the average life of a nucleus. That will be the average life of a nucleus in this arrangement. Obviously n0 will get cancelled. There is a t dt, sorry, there is a into t also. There is this t also. Now this lambda will come out, not a problem. What is it that we need to integrate? We need to integrate e power minus lambda t dt. T changes from 0 to infinity. Why did I teach you mathematics? How do you do this? No, not at all. You've forgotten all the mathematics that I taught you. I will not integrate this. Of course you can do it integration by parts. I'll differentiate this, I'll integrate this. Huh? No. So e power minus lambda t dt 0 to infinity. That's 1 by lambda, isn't it? That's 1 by lambda. Differentiate with respect to lambda both sides. Leibniz, differentiate with respect to lambda both sides. When I differentiate with respect to lambda both sides, then I'll get a minus t here, which is yes or no? So when I differentiate with respect to lambda both sides, then I get minus t e power minus lambda t dt 0 to infinity. That's minus 1 by lambda squared. minus goes away. So that's 1 by lambda squared. Now, t e power minus lambda t you could have differentiated by parts. But if I gave you a larger number, t to power 10, e power 10 times, you would have to apply integration by parts. Not fun at all, right? So it's 1 by lambda squared. So Leibniz was not a totally useless thing, right? Do you realize this is 1 by lambda squared? So now all that you need to do is plug in 1 by lambda squared for this. Lambda by lambda squared. What's that? 1 by lambda. Right? The integral is 1 by lambda squared. And there is a lambda sitting in here. So this integral T average, as you see, is lambda into 1 by lambda squared, which is 1 by lambda is the average life. This is the average life of a nucleus, 1 by lambda, 1 by the decay constant. What was half-life? 0.693 by lambda. Half-life, therefore, is 0.693 times average life, isn't it? What was half-life? Half-life was 0.693 times 1 by lambda. But 1 by lambda you can write as average life of a nucleus. T half, T average, 1 by lambda. So that's the relationship between half-life and mean life. Half-life and mean life. Now, all good so far? Can I wipe this off? Yeah. Can I wipe this off? Huh? So, like I said, n goes as n naught e power minus lambda t, right? Number of active nuclei at an instant of time t starting from n naught is this, right? N naught, right? In a time equal to t half. In a time equal to t half, the number of samples got reduced to n naught by 2. Number of samples got reduced to n naught by 2, right? Now, in a time t equal to t average, what is t average? T average is mean life, which is 1 by lambda. In this time, what was the living samples? How many samples were still intact? So, in this time, in a time equal to t average, the number of living samples would be n naught e power minus lambda. This t would be 1 by lambda, which is n naught by e, which 1 by e, have we encountered this number anywhere in capacitors? 1 by e? 0.37? 0.37 n naught. That means 30 in a time equal to an average life. In a time equal to an average life, this is 0.5 n naught. And which is more, t average or t mean? See, what is t average? T average is 1 by lambda. What is T mean? 0.693 by lambda. T average is more. T average. Sorry, T half. Sorry, T half. I'm so sorry. T half. Which is more? T average is more. T average is more, right? So T average comes here, right? This is T average. And in this time, the number of active samples would be 37% of N naught. N, number of active undecayed samples. This equation gives me what? Not the number decayed. The number that are undecayed. The actual active samples means undecayed samples of undecayed nuclei. Undecayed number of nuclei. N minus N naught will give me what? Number of decayed nuclei, which would have got transformed into a daughter nucleus. Now, this was a fairly simple radioactive decay that involved a parent and one daughter nucleus, right? But actually, in general, in reality, what happens is there is successive decays. One parent giving me one daughter. And then that daughter becomes a parent giving another daughter. And then that another daughter becomes a parent giving me another daughter, and so on and so forth, right? So there could be in general a successive decays. There could be set of successive decays with different decay constants, with different decay constants. Let's look at a decay from A to B to C. Let's look at that successive decay from A to B to C, right? But the basic rules of the game will remain the same, right? There is A, which transforms into B, which in turn could transform into C, right? The decay from A to B, has a decay constant lambda 1, say. The decay from A to B has a decay constant lambda 1. The decay from B to C has a decay constant lambda 2. Right? And at time t equal to 0, I start with N naught nuclei of A, N naught nuclei, unstable nuclei of A, N naught active nuclei at time t equal to 0. I start with A. But obviously, there is 0 and 0 of B and C at time t equal to 0. T seconds later, the number of nuclei of this becomes lambda n1. The number of nuclei of B will become n2, and the number of nuclei of C will become n3 at an instant of time t. Now, look at B. Rate at which A is getting decayed is the rate at which B is getting formed. But B is not just getting formed, B in turn is also getting decayed, right? So B decays into C. There is a rate of formation of B and there is rate of decay of B. There is a rate of formation of B and there is a rate of decay of B. Yes or no? Now, Rate at which A is decaying is what? Lambda 1 n1 is the rate at which A is getting decayed. Isn't it? Activity of A, rate at which A is getting decayed to form B at this instant would be proportional to the number of nuclei of A at this instant of time. So this is rate at which A is getting decayed, which is also the same as the rate at which B is getting formed. Rate at which B is getting formed. Right? Now, but B is just not getting formed, it's also getting decayed. What's the rate at which B is getting decayed? Lambda 2 n2. Lambda 2 n2 is the rate at which B is getting decayed. Yes or no? So lambda 2 n2 is the rate at which B is getting decayed. Right? Now there is, therefore, the difference of these two rates will give me the rate at which B is getting formed. Right? So rate at which B is getting formed, the net rate at which B is getting formed well, this is rate at which it is getting formed, lambda 1 n1, minus this is the rate at which it is getting decayed, which is lambda 2 n2. Lambda 1 n1 minus lambda 2 n2. That's the rate at which it is getting decayed. Yes or no? So this would be the net rate at which B is getting formed. This is the net rate at which B is getting formed. Yes or no? And so if this is the rate at which B is getting formed, that means this is the rate of change of n2 with time. Decays per second of n2. So this must be ddt of n2. This must be dD2 of n2. Yes or no? Rate at which B is getting formed, net rate at which B is getting formed is this. This is the rate at which A is decaying, which is the rate at which B is getting formed from A. But some of it is getting decayed because B is getting decayed to C. The rate at which B is getting decayed would dilute this. Yes or no? So minus lambda 2 n2. Are you all okay with this so far? And what's the rate at which C is getting formed? Rate at which B is getting decayed? Right? Rate at which B is getting decayed is what? Lambda 2 n2. And that must be the rate at which C is getting formed. That must be the rate at which C is getting formed. Yes or no? Okay. At t equal to 0, I had n0 nuclei of A, and I had at an instant of time t n1 nuclei of A remain undecayed. Is there a relationship connecting n1 and n0? What is it? n1 is n0 e power minus lambda t. Yes or no? n1 is n0 e power minus lambda t. What is my objective here? My objective is to find the number of nuclei of B at an instant of time t. I want to find n2 as a function of time. n1 I know as a function of time, which is this. Now, using this differential equation, I want to find n2 as a function of time. The number of nuclei of B as a function of time, undecayed nuclei of B. This is what I want to do, right? So, dn2 dt, I want to solve this differential equation. n1 I know is n0 e power minus lambda 1 t. This is lambda 1. n1 is t minus lambda 2 n2. I want to solve this differential equation. n2 as a function of time. How do I solve? I want to find n2 as a function of time. How do I solve this differential equation? Yes, it's a linear n to transpose this on this side. dn2 dt. Good, Divyan. Plus lambda 2 n2 is lambda 1 n naught e power minus lambda 1 t. Do you realize it's a linear in n2? It's a linear in n2 and I know how to solve it. You also do. Right? Let's e power integral p dt. Instead of dx, I'll have p dt. This is my p and this is my q. And instead of dx, I'll have dt. That's the only difference, right? Lambda 2t, right? p dt is integral lambda 1 n naught e power minus lambda 1 t into e power lambda 2 t dt. Right? P e power integral q dx, right? Q e power integral p dx dt. So this gives me n2 e power lambda 2t equals lambda 1 n naught. This is e power lambda 2 minus lambda 1 t e power mx by m. But there is a constant of integration here. There is going to be a constant of integration which I need to obtain. Isn't it? This is what happens when I integrate. Now, at t equal to 0, what was n2? 0. See, at t equal to 0, there was nothing of b, right? So, no. At t equal to 0, n2 is 0. What is c? C is minus lambda 1 n naught by lambda 2 minus lambda 1. That's c. This is 0, but this is not 0, 1. So minus lambda 1 n naught by lambda 2 minus lambda 1. That's my constant of integration. Right? So that gives me n2 e power lambda 2t. On plugging in c here, I get lambda 1 n naught by lambda 2 minus lambda 1 e power lambda 2 minus lambda 1 into t minus 1 is what I get. Plugging in c and taking lambda 1 n naught by lambda 2 minus lambda 1 common from the whole thing. Does it make sense to you? I just plugged in the value of c that I obtained in this equation, n2 e power lambda 2t, and I took lambda 1 n naught by lambda 2 minus lambda 1 common from the whole thing. Now let me multiply by e power minus lambda 2t throughout, e power minus lambda 2t. So that gives me n2 equal to lambda 1 n naught by lambda 2 minus lambda 1 e power minus lambda 1 t minus e power minus lambda 2 t is what I get.